Hello dear friends, welcome to my channel. Today's discussion is deflection of beam. Consider a uniform beam as made up of fibers running lengthwise. We have to find its deflection under given loading. In bent form, the fibers of the lower half are stretched and those of upper half are compressed. In between these two, there is a layer of unstrained fibers called neutral surface. Okay, so there is a layer of unstrained fibers called neutral surface. The fiber which was initially along the x-axis, the central horizontal axis of the beam, now lies in the neutral surface in the form of curve called the deflection curve. Okay, the form of curve is called deflection curve or elastic curve. We shall encounter a differential equation while finding the equation of the curve. Consider a cross section of a beam cutting the elastic curve in P and the neutral surface in the line AA dash. Okay, AA dash, this line. So AA dash, this line is neutral surface. Okay, this line is called neutral surface. Neutral axis of the section. It is well known from mechanics that beam moment M about A dash. Moment M is equals to beam moment about M dash. About M dash, sorry, M dash, not A dash, sorry, A dash. So beam moment about A dash of all forces acting on either side of two portions of the beam separated by this cross section. So A dash, this line is neutral surface. Okay, this line is called neutral surface. Neutral axis of the section. It is well known from mechanics that beam moment M about A dash. Moment M is equals to beam moment about M dash. About M dash, sorry, M dash, not A dash, sorry, A dash. So beam moment about A dash of all forces acting on either side of two portions of the beam separated by this cross section. So friends, M equals to EI by R. This formula is Bernoulli-Euler law, and where E equals to modulus of elasticity of the beam, I is equal to moment of inertia, R equals to radius of curvature of the elastic curve at Px, y, and where M equals to beam moment about A dash is neutral surface. Now R equals to 1 plus dy by dx whole square to the power 3 by 2. So M equals to, we get, so whatever we get M equals to equals to EI divided by d square y divided by dx square, as R equals to R equals to 1 by d square y divided by dx square. So dy by dx equals to 0 when small deflections, or small deflection. Okay, I hope it is clear. This is my bending moment, and shear stress equals to dm by dx. This is called shear force. Shear force is equal to EI dqy divided by dx cube, and intensity of loading means d square m and divided by d x square is equal to EI d to the power 4 y divided by d x to the power 4. So I hope I can clear these three facts. Okay, now convention of sines, the sum of the moments of about section n dash. I have already told that n dash in this figure, this is n dash, this is the neutral point. So n dash, due to external forces on the left of the section, if anti-clockwise is taken as positive, means anti-clockwise is positive and anti-clockwise is positive, and clockwise is negative. This is the sign convention. In condition, the arbitrary constant appearing in the solution of the differential equation 1 for a given problem are found the following condition: at a freely supported end, there being no deflection, no bending moment. This is this case, no bending moment. Figure 2, you will see, I discuss figure 1 and figure 2, you see that no deflection and no bending moment. We discuss this portion, this equation, no bending moment, and no bending moment, no deflection, because freely supported end, no deflection. So friends, when no bending moment, no deflection, so this means d square y divided by dx square equals to 0, and y equals to 0. At y equals to, we have y equals to 0 and d square by dx square equals to 0. At a horizontal fixed end, for this figure horizontal fixed end, for this figure, the deflection and the slope of the beam being 0. So in here y equals to 0, so dy by dx equals to 0. So okay, at a perfectly free end, there being no bending moment or shear force, we have d square y dx square equals to 0 and d square dq y dx cube is equal to 0. So friends, this is my total discussions, because this portion is very important for the radius curvature, because radius curvature is 1 plus dy by dx whole square to the power 3 by 2 divided by d square y divided by dx square. And when deflection is very small, then r equal to 1 by d square y divided by dx square. So I get the equation. Which equation? M is equal to ei d square y by dx square. Thanks for watching, friends. I hope I can clear this concept, because as I solve one problem based on bending moment, deflections of beams.